Hi, welcome to What's the Probability that your probability calculation is very wrong? Okay, so when probabilities are quoted in real-life situations, they're often treated as exact. But probability calculations have uncertainties and limited ranges of applicability. So here we're going to talk about a general class of scenarios where it's important to keep in mind that probability calculations typically are not exact. This definitely isn't the only type of scenario where it's important to keep that in mind, but it's what we're going to focus on here. Okay, so here goes. Let's say you calculate the probability of some event happening. You get a very small number, and then that event happens. If we take the probability calculation as exact, then we will conclude that you just witnessed a very rare event. But what if the probability given by the calculation is smaller than the probability of getting the probability calculation substantially wrong? To illustrate, first let's look at a toy example. Let's say there's some class of event whose probability you need to predict, and you have a method for calculating these probabilities. This method gives results that typically have error bars of about 1% relative. So say it might give a result of 50 plus or minus 0.5%. The size of the error bar works great for your applications. But let's also say that for about 1 in every 1,000 cases, your method is simply not applicable. In these cases, it gets the probability very badly wrong. And let's also assume that there's no way to tell ahead of time whether a specific calculation is going to fall into this category where it messes up badly. Also, let's say the cases when it's wrong are uncorrelated with the value of the probability that it reports. So you can't look at the result and say something like, this number is very large or very small. This must be one of the cases where it screwed up. And furthermore, let's assume that when it's badly wrong, you have no idea what the correct probability is. The correct number could be large or small. Now let's look at two cases. In case 1, let's say you do the probability calculation for some event and you get 30%. It has a 1% relative error bar, so that's 30 plus or minus 0.3%. Then that event happens. So your calculation gave a relatively large probability of that event to happen, and it happened. Nothing seems odd about this. Now it's possible in this instance that this was one of those 1 in 1,000 cases where your probability calculation was badly wrong. But there's no compelling reason to believe it was. Okay, now let's look at case 2. This time, let's say the probability calculation returns a very small value, 1 in 10 to the 6, 1 in a million. Then that event happens. Did you just witness a 1 in a million event? Or was the probability calculation just wrong? Remember, we said that the calculation gets 1 out of every 1,000 results wrong. Chances are the calculation was just wrong. In case 1, where we had a 30% probability, it was very easy to neglect the probability that the calculation is wrong. If situations like this are typical, it is very easy to forget these errors happen and round 1 in 1,000 down to 0. Problems happen if this rounding down occurs and then a situation like case 2 pops up. If we forget that these errors can happen, we can incorrectly believe an extremely rare event happened when we instead had a somewhat rare or even merely unusual calculational error. Okay, now let's move on to some slightly more complicated examples. Example 1. Let's say you have a set of radioactive samples that you use for classroom demonstrations. You have asked your graduate assistant to get a sample from the cabinet and set up the demonstration for today's class. You wish to show how the number of radioactive decays in a given time period is well described by the Poisson distribution. Your graduate assistant has set up this demonstration more than 50 times, without fail. You have also been doing these demos for many years, and you're quite proficient at them. Given how many times you've done these demos, you think the probability that something would go wrong is fairly small, maybe a few percent. Now, let's say you do the demo, and embarrassingly, you get a result that differs substantially from the prediction. In fact, it differs so much that, if the prediction is correct, the probability of getting a result as weird or weirder than this one is less than 10 to the minus 5. Now, it's possible that you observed a very rare event. But it's more likely that your graduate assistant didn't prepare the sample properly, or that the sample was incorrectly labeled, or that the measuring equipment failed, or that you made a mistake during the demonstration. If you've done many of these demos without fail, it could be easy to forget that these possibilities exist. We said that you thought the probability of a problem arising with a particular demo to be a few percent. So here, if you've had a lot of successful demos, it's not hard to round those few percent down to 0. So while it's possible that you observed a very rare occurrence, it is much more likely that something occurred to make your prediction wrong. Okay, example 2. Your dog is sick and you take it to the veterinarian. Your veterinarian recommends a treatment. She says that approximately 1% of dogs have an adverse reaction to the treatment. Given your dog's illness and the likely benefits of the treatment, a 1% risk of an adverse reaction seems like a reasonable risk to take. But let's look at the following scenario. Say that, in fact, 1% of dogs given the treatment have been observed to have an adverse reaction. But let's imagine that the prevalence of the adverse reactions is highly breed dependent. Some breeds have a very low rate of adverse reactions, like 0.1%. Others have high rates, like 20%. And unfortunately, there is no information on your dog's breed. In this case, it is possible that your dog's breed has a high rate of adverse reactions. Here, although the 1% number is correct for dogs who are given the treatment on average, it might not apply to your dog. So the question becomes, given this dependence of the rate of adverse reactions on the dog's breed, what is the probability that the 1% number is a large underestimate of the risk. Here, the probability that the probability calculation is wrong may be important. We don't have enough information to tell in this case, but it's possible that an adverse reaction in your dog would not be a 1 in 100 event, but instead that the 1 in 100 number is simply not applicable to your dog. So more information would be desirable in this situation. Okay, lastly, example 3. Say you have a piece of equipment which you have used for many years. You're an expert at troubleshooting it. The equipment has an onboard computer with self-diagnostics to tell you when something has gone wrong. Sensors report back to the onboard computer when the respective components they monitor fail. Now, some parts on the equipment experience constant wear and have to be replaced regularly. So this kind of error happens all the time. When the self-diagnostic tells you that one of these parts needs to be replaced, you perform the repair. But today, the equipment refuses to start without warning. A sensor reports that a critical component has failed. The onboard computer will not allow the equipment to start, as it could be damaged if run without this component functioning properly. You've never seen this component fail before. To learn more, you contact other people who also use this equipment. None of them has seen this type of failure before either. It seems to be quite a rare failure. Because this is a rare failure, it might make sense to consider the possibility that the critical component is actually fine, but that the sensor reporting the failure is faulty. So let's say that in this scenario, there are 3 types of failures that can happen to the equipment. First, there can be a common failure. This is the type of failure that happens with parts that quickly wear out and need to be replaced. These happen all the time. Next, we have rare failures. A failure of this critical component would be an example of a rare failure. And finally, we have failures caused by a sensor going bad or other diagnostic problem. In what follows, I'll simply call this last set sensor failures. So let's imagine the following. Let's imagine that common failures happen way more frequently than sensor failures, but sensor failures happen way more frequently than rare failures. So in a given time period, the probability of a common failure, here written as P of common failure, is much higher than the probability of a sensor failure, and the probability of a sensor failure is way higher than the probability of a rare failure. So, given those conditions, let's look at what happens when a common failure is reported and what happens when a rare failure is reported. Note here that we mean that that type of failure is reported by the onboard computer, which does not necessarily mean that that type of failure actually happened. When a common failure is reported by the onboard computer, the probability that the problem was incorrectly diagnosed, or in other words, the probability of a sensor failure, is much smaller than the probability that the failure reported by the computer actually happened. On the other hand, when a rare failure is reported by the computer, the probability that the problem was incorrectly diagnosed, because there was actually a sensor failure, is much larger than the probability that the failure reported by the computer actually happened. So this means that when a common failure is reported, it is easy to neglect the possibility that the problem has been incorrectly diagnosed. On the other hand, when a rare failure is reported, the probability that the problem has been incorrectly diagnosed should not be neglected. In this scenario, the event we observe is a sensor telling us that a failure has occurred. If we see a lot of common component failures, it is really easy to approximate the probability of a sensor reporting a component failure as being equal to the probability that that component actually fails, neglecting the possibility of a sensor failure. A more accurate statement would be to say that the probability that a sensor reports a component failure is equal to the probability that that component actually fails, or that a sensor fails in such a way as to incorrectly report that that component failed. In the case of a common component failure, the previous approximate expression will give results pretty close to this one. On the other hand, if we consider rare component failures, equating the probability of a sensor reporting that component failure and the probability of the component actually failing is badly wrong. But if we usually see common component failures, it is easy to forget that this relation isn't always okay. In other words, if we see a lot of common component failures, it is easy to round the probability of a sensor failure down to 0. If we use this formula as our probability calculation, we will think we've seen a rare component failure when we've probably seen a merely unusual sensor failure. Okay, let's summarize. In real life, probabilities are often quoted as if they are exact quantities, ignoring uncertainties or ranges in validity. But it's important to remember that this is an approximation, and here we've looked at one set of situations where this can be important. If we regularly use a probability calculation that tends to yield largish numbers, it is easy to ignore small effects that can occasionally make our calculation significantly wrong. And if we ignore these effects long enough, it's easy to forget that they even exist. If our probability calculation subsequently gives a tiny value, it is far too easy to ignore these effects, which may no longer be negligible. This doesn't mean that we should distrust probabilities. Instead, it points out that when a calculated probability is tiny, sometimes possibilities that you would normally ignore can become important. It's important to recheck one's assumptions, and if the probability that the calculation is wrong is comparable to or larger than the calculated probability itself, extra care is definitely needed.